In the last video I explained how to draw a perpendicular line from a point, C in this case, to a given line, AB in this case. We did it by drawing two circles, centered at A and centered at B. Now in this video I want to prove that the angle between CD and the line AB is 90 degrees, so it's called alpha here. We're going to do a proof by contradiction. We're going to suppose that C prime is the image of C under axial symmetry in the line AB, where C prime is not equal to the point D. So we're going to get the image of this point C under axial symmetry in this line. So here is the picture. Now it looks obvious from the picture that C prime is not the image of C under axial symmetry in the line AB, but we are going to pretend that it is. C prime is the image of C under axial symmetry in the line AB. The thing about the point C prime is that it's not equal to D, so it can't be on both circles. It could be on one of the circles. I've shown it on neither of the circles, but I could have shown it on this circle here or on this circle here, but I can't show it on both circles. We are going to show that this statement leads to a contradiction. Well, since we have axial symmetry, we should find that the line joining B and C is equal in length to the line joining B and C prime, because after all, axial symmetry preserves lengths. So the image of BC under axial symmetry in the line AB should be a line with the same length. Similarly, the line joining A and C should equal the line joining A and C prime. So this is the picture that we should have if C prime is indeed the image of C under axial symmetry in the line AB. But of course, since C prime is not equal to D, it's not on at least one of the circles. So the distance of the center of one of the circles to the point C prime is not equal to the radius of that circle. And if that distance is not equal to the radius of one of the circles, then that distance is not equal to one of these two distances. So our original statement has led us into a contradiction. So our original statement must be false. So it must be false that if C prime is the image of C under axial symmetry in the line AB, then C prime is not equal to D. So if this is false, then C prime must equal D. So that means that D must be the image of C under the axial symmetry in the line AB. And by the definition of axial symmetry, we know that the angle between this line and the line AB must be 90 degrees. So alpha must be 90 degrees. In the last video, we saw how to construct the perpendicular bisector of a line segment. So we're looking at line segment AB, and the perpendicular bisector is DE. We drew two circles of equal radii centered at A and B. The radius of each circle is more than half the length of the line AB. We know from the previous part that this line is perpendicular to AB. So all we have to do now is prove that AF equals FB. We have two right angle triangles formed here. So I'm using Pythagoras' theorem. We will prove this in another video. But for now, all you need to remember is that if we get the sum of the squares of the two short sides of a right angle triangle, that will equal the square of the longest side. So in this right angle triangle here, AF squared plus FD squared will equal AD squared. Similarly, for this other right angle triangle, we have that FB squared plus FD squared equals DB squared. But we can see that the long sides of both of these right angle triangles are the same. They're equal to the radius of each of these circles, and the radii are the same. So AD squared equals DB squared, or AD just equals DB. So that means that AF squared plus FD squared must equal FB squared plus FD squared. And we can just cancel FD squared from both sides, and we end up showing that AF squared equals FB squared, or AF equals FB. So we've proven that the distance of A to F is equal to the distance of F to B.